Okay, so part 2, and of course still with Mladen, and maybe even more so. Okay, and we talked about this this condition for actions, and the way it's usually proven is not as the existence of a family of maps, but as the existence of a family of covers. So I want to define this, and to this end it's useful to introduce the following definition. So G space, then say a subset is an F subset for some family of subgroups F if there exists a subgroup in F such that if we move the subset and still get intersections, then the group element was from F. So it doesn't happen too often. And if it happens, then we're inside one of the groups we're working relative to. Okay, and then we say an F cover is a cover by F subsets. Okay. And then now, so our condition, if this action has this regularity property, can be rephrased as saying the following: for every large number R, there exists a G invariant F cover of, and now we look at G times X with the diagonal action, and the cover should be finite dimensional, and for all points in this product there is a member of the cover such that if I take the ball of radius R on the group, so we need to fix some length function on the group, times, and then the second coordinate with just 1 point, we're inside of U. Okay, so this is kind of like finite asymptotic dimension, right, on the G coordinate, and in the X coordinate, I mean, continuous. Okay. Okay, and this, in order not to have to write this again, we'll say U is R wide for the second statement. And the translation is not very complicated. So if you have a cover, you can get a map to the nerve, and then you restrict to the slice unit element times X, and the restriction to this slice will be the map Fn, and then you have a sequence of covers, so you get a sequence of maps, and this condition 2 translates into the maps being more and more equivariant. Okay, and one advantage of this is that it allows us to sort of split up the space into parts and produce the cover on one part and then on the other part. Sorry? Oh, well, I usually wrote this differently, but this is fine. You can just, if you have this, you can just replace U with F times U. This only decreases the dimension, and then you have the property you're after. Okay. You're right. I mean, yeah. Usually I state this differently. Okay. Okay, so if our space is a union of two spaces and we know the condition for the two pieces, then we know the condition for the whole space. Under a mild condition, the space X should be metrizable in order to able to extend open subsets from X0 to X and so on. Okay, good. And so in our case, this allows us to restate. I have to switch to the second talk. To restate what we need to do. Okay. Right. So originally the statement was about the action of the mapping class group on the compactification of Teichmüller space. Teichmüller space itself is a GCW complex. So we're fine on Teichmüller space itself. So we only have to consider the boundary. Okay. So we need to find an n such that for all r 0 there exists an f being the family we discussed, the family that virtually has a fixed point. Cover u for the mapping class group times the boundary such that the dimension is less than n and 2 the cover is r wide in this sense. Okay. Okay, and we'll need some facts from Teichmüller geometry. What? This is I'm not allowed to do Teichmüller geometry, or okay, so Teichmüller space has a natural metric. I mean, there's more than one natural metric, but the one we're interested in is the Teichmüller metric. Okay. And one important property of it is it allows for unique geodesics between any 2 points. Okay, and moreover, PMF, so our boundary, okay, so if I have a point on the boundary and a point interior, I know in which direction this point on the boundary is, and this furthermore allows us allows the following construction. So, oops. Whenever I have such a pair, I get a geodesic Teichmüller ray. I'm going to call it CXC in Teichmüller space. I mean, it's not. It starts out. It's not. I mean, the metric is not a Riemannian metric. But nevertheless, basically what you're saying is true. I mean, Teichmüller space is. I mean, it's R to the blah and so on, and this is the. No, it's just not a Riemannian metric. I mean, it's. I think it's a Finsler metric or. But Teichmüller space is contractible, and you can get it this way. But it is different than the non-positively curved case, as was already pointed out at the end of the first talk. Namely, so for us, bad news. And I mean, we might expect, if we take our ray and let t go to infinity, that we end up with the point in the direction we're going at. But that's in general not true. Okay, so I mean, the points at infinity parameterize the geodesic rays starting at x, but they don't necessarily end up at those points in. Yeah, this doesn't. I wrote bad news. I mean, so you know, it's kind of bad, right? So this is very different from what we're used to from non-positive. Pardon me? No, it doesn't. I mean, it may accumulate. So it doesn't converge to one. And it's actually, I mean, the question is, I mean, I briefly talked about how to think about these points as PMF, and there's sort of the foliation and the measure, and it's only the measure that's in question, right? I mean, the foliation is fine. We're hitting the right foliation, but the measure is not really, doesn't really work out. Okay, but there's also good news, of course. So if we don't, I should have defined something that I, pardon? No, it determines. I mean, there's a construction, and I sort of hinted at the construction when I've drawn this box here. Yeah, there is a construction, so there's a map that, given any pair of points, there is a geodesic ray. It's just the construction doesn't have this property. I'll give you properties, okay? I mean, it's really, I mean, it's a construction. PMF, you identify with the directions given at a point, and you follow this direction. That's the construction. Okay, so I forgot something important. Maybe I'll just do it here. Sorry. So. The action of the mapping class over Teichmüller space is not co-compact, as already pointed out, and then, but one still has a thick part. So for every positive number epsilon, we look at the epsilon thick part, which is those points in Teichmüller space that the length of every curve is at least epsilon. So there are no too short curves. There's a bound on how short the curves get, and here the action is co-compact. Okay, and the good news is that as long as we stay in this co-compact part, the behavior is much better. Yeah, yeah, but it's the same sort of thing everywhere. I mean, thick, thin decompositions, you know, yeah. I mean, there's a thick, thin composition also for Riemann manifolds or for outer space, and I mean, there are lots of instances of this feature. Well, I mean, the curves are simple closed curves on the surface, okay, and then, but then once we pick a point in Teich, well, they're homotopy free homotopy classes of simple closed curves, and then once we pick a point in Teichmüller space, we pick the corresponding geodesic with respect to this metric and take its length. Okay. Okay, so geodesics. So as long as we stay here, they behave like geodesics ought to behave in a hyperbolic space. And let me give you two statements. Yeah, yeah, there are. Right. I give you two statements and then. Yeah, it's a geodesic ray. But I mean, well, they may or may not. Some do, some don't. Okay, so Maser proves, sorry, if the ray stays inside the thick part, then we don't have this problem. Okay, and Minsky proved the following hyperbolic behavior of these rays. So, I mean, if depending on the thick part I'm working with, I get a constant d, such that for all cases where we stay in the thick part, they are decontracting. So this means the following. So we have our geodesic or our geodesic ray, and we look at any ball. So this is any ball. I mean, the radius is not bounded, but it does not, I guess I got it wrong, does not intersect the geodesic. And then we take the closest point projection, and in hyperbolic spaces looks like this, right? Things get collapsed, and that's the requirement. So the diameter of this is at most d. Okay, so that's one way to sort of phrase that the direction is hyperbolic if it has this feature, and Minsky proves the directions that stay inside the thick part have this property. Okay. Okay, so now we pick a base point in Teichmüller space and let our rays start from there. And then we define. Right, remember, we're interested in covering this space, and we can now split it up in a thick and a thin part. So the thick part is all pairs such that the geodesic issuing from G times our base point and trying to go to Xi stays in the thick part, and maybe less where it doesn't. Okay, and then we need to prove two things. The first is about the thick part. So there is a number for the thick part, such that for all r and for all epsilon, I'll find a v-cyclic cover for the thick part. With the two properties we want, the dimension of is at most this number, and it is R white on this subset. Okay, and then we need a corresponding statement for the thin part. So there's a number n thin such that that for all r, now there exists an epsilon, here we had for all, and then there exists an f cover using for the thin part. Again, with 1 and 2. Okay, so if you want to prove theorem B, we're giving a large number R. We need to find the cover. We first do the thin part, so some thin part we can cover. Then we're left with some thick part, but any thick part we can cover, so we're fine. Okay, good. And so these two properties are what's used to prove proposition 1, the thick part cover, right? Because their geodesics behave hyperbolic. That's what this says. And then the technology we had from hyperbolic groups and so on can be adapted to work here. Okay, so I don't plan to say more about this. It's kind of the old technology. Okay, so we're left with the thick part, and I want to okay, so I mean, this was, so we had So Teichmüller space is when the compactification is this, and we said that, I mean, on a GCW complex, we always have maps in our space, right? I mean, even equivalently. So it's GCW complex is kind of the perfect space for our properties, but it's usually not compact. And we compact for it by adding something, but I mean, the property doesn't get lost on T, but it's going to be difficult on the rest. That's why we only have to look at the boundary. Okay? I mean, this is why it's good to talk about covers, right? Because I mean, you cover this, and you just extend it a little bit to the inside to make it open on the whole space. And I mean, the dimension of the cover, then I mean, you add the dimension of the two covers, maybe +1 or something. So it's right? With covers, it's convenient. It's easy to glue. With maps, you would have to think, I mean, how do I glue these maps? But with covers, it's clear. You just put them together, and there's only the issue of extending this from this closed subset to the whole thing. But that's, I mean, you just extend it a little bit. Okay? Good. Okay, so the tools to prove the second proposition, the one about the thin part, is our subsurface projections, or the projection distance of Maser-Minsky. Okay, let me try to roughly say what this theory does. So if you travel in Teichmüller space, and you want to know how you make progress, and Maser-Minsky have a theory that sort of says at each time you're making progress, maybe not over the whole surface, but only over certain subsurfaces. Right? So you really only right. I mean they give progress means actually we travel, we move. Okay, I didn't want to give the formal definitions, but let's try. So I mean you have Teichmüller space and you have a subsurface. Okay, and then you have a map. I mean, given for the subsurface, you have the curve complex. I mean, a priori you have this curve for the whole surface, but you also have the curve complex for the subsurface. Okay, and then you can map a Teichmüller space to all these curve complexes. Okay, and if you have a geodesic in Teichmüller space, they map then to all these curve complexes, and you can look. I mean, are they geodesics or not, or how do they behave? Okay, and you know, if the distance in Teichmüller space is more or less the same as in a certain curve complex, then we're saying we're making progress over this subsurface. That's what their theory does. I mean, it's a complicated theory, but it relates sort of, it gives different distances on Teichmüller space sort of different flavors. It relates them to subsurfaces, right? Ah. Huh? the curve the curve complex you've surely seen. I mean, the curve complex is you build a complex by looking at all curves. I mean, you have a surface. You take as a vertex set all curves in the surface, and you put an edge if they're disjoint, and that's the graph, and that's the curve complex. I mean, you can make it also complex, but we're only interested in the graph. And one of the big things is theorems of Maser-Minsky is that this complex is hyperbolic. Okay, I'll get to a toy model of this, but not to the actual theory later. Okay, so this is this, and the other is the projection complex of Bestvina, Bromberg, and Fujiwara, which kind of organizes all this data in the Maser-Minsky theory in a better way, and is then used to prove their result on a finite asymptotic dimension of the mapping class group. Okay, and I only want to discuss a toy case, namely the action of SL2Z on the boundary of hyperbolic space. So this is really only a relatively hyperbolic situation. Okay, so it's considerably easier. Okay, so we have H2, but we have the same feature that the action of SL2Z on hyperbolic space is not co-compact. And how do we make it co-compact? We look at a thick part, or in other words, we remove horoballs. All right, so this is okay, and kind of like over here, we're fine if we stay outside of the horoballs, but if we go into the horoballs, then we have to use the structure of the horoballs to produce our cover. Okay, and it's slightly easier to work with a combinatorial alternative, namely the Ferry graph. Okay, and so let's pick a base point. Oh, I need later a base point. So in this model, the subsurfaces of Maser-Minsky, they parameterize horoballs in Teichmüller space. So these horoballs that are relatively easy over here. Okay. So these are one-to-ones corresponds to the horoballs, which in this combinatorial picture we translated to the vertices of the Ferry graph. Let's call him gamma. Okay. The projection distance. So there are now various versions of it, between what different things we want to take the projection distance, but I want to take it between a group element and a point, and a point on the boundary. Okay, and to this end, we fix one of these vertices as the base point, and maybe over here I have my point on the boundary, and then we look at the geodesic. Let's say this is gx naught, and then I take the geodesic from here to here and look which edges of the graph does it intersect. and to make up the distance with respect to y. Y might be this point here. So in this case, the distance would be 3 because it intersects 3 edges that are incident to y. Okay. So okay, and this kind of measures how long this this geodesic travels through the horror ball corresponding to y, right? And this is exactly what we're interested in because being in the horror ball means being outside the thick part. Okay, and technically we put as a y to be infinity. Sorry, you seem unhappy. Pardon? Right. I mean, they're right. I mean, they're right. I can draw more here and pardon? Yeah, I can draw more in y, but I mean, they're here. They don't intersect anymore. Right? I don't get the red stuff. yeah. Right. It was. I mean, it was important that this. Yeah. It was important that this point. I mean, was a vertex. No. I mean, the Ferry graph is. I mean, you start with this geodesic triangle and reflect it around. It is this picture. Okay. Yeah. It's not just any. It's this picture. Okay. Right. And so and what this measures is this red. I mean, if we translate over here, it kind of measures how long this curve goes through the horror ball corresponding to y. Okay. Okay, there's one more translation. So we were interested in the, well, let's say, thick part. This translates to all those pairs where this projection distance doesn't get too large. So this is for all y. So the other way around, and that's really what I should have said. If we're in the thin part, then there exists